Hello viewer and welcome to the e-learning classroom. So today we want to look at the practical on current. We have voltage and also we are plotting a graph of E minus V against high. That is the graph we are going to plot, and then we will be able to determine the internal resistance of the cells using the graph. So we'll first arrange the apparatus as they appear. So we have a cell holder. Maybe we can put some cells in the cell holder. Can input some cells. So we have a cell holder here. Let's input some cells there. So we have some cells in a cell holder. So we have the cells on the upper part. Then from there we have a voltmeter. Maybe the voltmeter is somewhere here. We have the voltmeter there. We have a switch. So the switch is somewhere aside, somewhere here, close to the cells. We have the switch. This is the voltmeter and the cells. Then we have the ammeter somewhere down here. We have the ammeter. This is the ammeter somewhere down here. And then from there, we have the nichrome wire. This is the wire we are going to use here, the nichrome wire. Our scale is from 0 to 100 for the nichrome wire. So once we have done that, that is how the cells are arranged, the setup. Maybe we can take away this one. So we have arranged the apparatus as they appear in our diagram. So, and once we are done with that now, we look at the arrangement of the circuit. So we'll start from the positive terminal here. So from the positive terminal, one wire is going straight to the switch. So from the positive terminal straight to the switch. So let's see. The first wire from positive terminal. Our positive terminal is here. So from the positive terminal, this wire goes straight to the switch. So from the positive straight to the switch. Then from the switch, we have another wire coming from the switch. Another wire coming from the switch. This is the wire coming from the switch. And this wire, they become two here at the junction, so that one goes to the voltmeter and one to the ammeter. So we have a junction of two wires. So we make a junction there of two wires. So maybe at this point, can make this junction. So let's see how we make that junction of two wires. We have the junction there. And then these are the two wires now. And then one wire goes straight to the ammeter. Because we are from positive terminal, so we'll put it on the positive terminal of the ammeter. That is the red one, to the positive terminal. And then the remaining one straight to the voltmeter. Again, we can also connect to the positive. Again, we can connect to the positive of the voltmeter at the 5 volt. That is at the 5 volt terminal. So we are there. We are up to this junction now. Then one wire from the ammeter to 0 of the nichrome wire. one wire from the ammeter. So for the ammeter we can use 0 to 3 ampere. That is the scale of 0 to 3. 0 to 3 there. Zero to 3 ampere, and then this wire goes straight. This wire goes straight to the 0 of the ammeter, or 0 of the nichrome wire. The 0 of the nichrome wire. So let's input that. We have put it there at the 0 of the nichrome wire. So from there now we have we go back to the negative terminal. Remember our apparatus, we have arranged them as they appear in the diagram. So from the negative terminal we have one wire coming out. From the negative terminal we have one wire. And then once it comes out, we have a junction of 2 wires. So that one wire goes to the voltmeter and the other wire goes to the one goes to the voltmeter and the other one to the nichrome wire. So let's make that junction. There's a junction of 3 wires. 3 wires there. We have the junction here. These are the 2 wires coming from there now. The 2 wires from this junction here. One wire goes straight to voltmeter. So for the voltmeter we can put the negative side, because we are on the negative terminal. So one wire goes straight to the voltmeter. The other one goes straight to the nichrome wire. That is the mobile wire now. So maybe we can input it at the 20 centimeter mark. We can input it at the 20 centimeter mark there. You can see now all of them are already giving some reading. Both the voltmeter and ammeter have got some reading now. Maybe we can first disconnect here, but you realize already there's some reading for both the voltmeter and the ammeter. There is already some reading for both the voltmeter and the ammeter. So maybe let's see again the readings how they appear. So maybe for the ammeter, we can change the scale for the ammeter, because you realize the diffraction is very minimal. Let's work with the scale of 0 to 1. Remember, the scale of 0 to 1 is more accurate than the scale of 0 to 3. Because you realize the deflection is very minimal and we require some significant diffraction. So we have changed for the voltmeter. Let's see now. Yeah, at least now we have some larger diffraction, some significant diffraction. So once we have that now, what we do, we go straight to, first of all, we have to understand the scale readings of the voltmeter and the ammeter. So we have the ammeter here. The scale reading we are using is 0 to 1. That means 10 divisions 0.2. 10 divisions is 0.2. Hence, one division is representing 0.02 ampere. That is the accuracy. For the voltmeter, we have a scale of 0 to 5. 10 divisions is 1. That means one division is 0.1 volts. these are the accuracies. The accuracies of the scales we are using. So let's start now. What we can do now, we can close the switch. Maybe we can close the switch now. Once you have closed the switch, we can open, the circuit is now complete, meaning current is flowing in the circuit. But let's first disconnect the switch so that we have only the ammeter giving some reading. So let's first disconnect the ammeter so that we can only have the voltmeter giving some reading. We disconnect the ammeter only so that the ammeter is not reading. So the reading there is 3.0 volt, and that is now the EMF. The EMF is equals 3.0 volt. Remember, EMF is the reading of the voltmeter when no current is flowing in the circuit. The reading of the voltmeter when no current is flowing in the circuit. So that is 3.0 volt. So with that now we go straight, and now we now check, we close back the switch, meaning now the current to flow in a complete path for the ammeter. So what we do, let's start with the reading at 20. When the pointer is at 20, so for the voltmeter we're using the lower scale, which is 0 to 5. That means we have 17 squares, 17 divisions, 17, and each division is representing, we have the accuracies here. Each division is representing 0.1 volt. So 17 times 0.1 is 1.7. So that means voltage is 1.7. Then we have current. Current, we have the number of divisions is 20. We are using the upper scale, so there are 23. So 23 times each division is 0.02 ampere, which is 0.46 ampere. 0.46 ampere there. So we go now to the next one at 30. So we move our scale up to 30. We move it up to 30. We don't have to disconnect, we just move it directly. So at 30 there, let's start with the voltmeter. These are 17 divisions times 0.17 times 0.1, which is still 1.7. Then for the ammeter we have 19. So 19 times 0.02, which gives us 0.38. 0.38. We go to 40. So we adjust up to 40. For the voltmeter, we have 2.0. Already it's indicating very well. 2.0. Then for the ammeter, we have 15 divisions. So that means we have 15 times each division is 0.02, which gives us 0.30. 0.30. We go to 50. So we adjust all the way to 50. We adjust all the way to 50. For the voltmeter, we have 21 divisions. So that means we have 2.1. 21, that is 2.1. For this side we have 13. So that means 13 times 0.02, which is 0.26. 0.26. We go to 60. We go straight to 60. We go to 60 there. So for the voltmeter, we have 22. That is 2.2. That is 2.2. Then for the ammeter, we have 11, sorry. We have 11. So 11 times 0.02, which is 0.22. 0.22. We go to 70. We are just up to 70. So for the voltmeter, we have 2. It is still 2.2. For the voltmeter, it is still 2.2. Then for the ammeter, we have 0.5. No, 0.2, sorry, 0.2. It is straight 0.20. 0.20, straight at 0.20. We go to 80. Let's go straight to 80. We are at 80 now. So at 80, let's get the voltmeter and ammeter readings at 80. So for the ammeter, we have 2.3. For the ammeter, we have 2.3. For the voltmeter, sorry, for the ammeter, we have 9 divisions. That means 9 times 0.02, which gives us 0.18. 0.18. So these are the values we have. These are the values we have now. For that practical, we are going to use these values to plot a graph. So we can now complete this table now using the values we have obtained. So let's start with E minus V. E minus V. So the first one is EMF is 3.0 minus V is 1.7. 3 minus 1.7, that is 1.3. Similar case here, 1.3. This one is 1.0. This one is 0.9, 0.8, 0.8. Lastly here we have 0.7. 0.7. Those are the values we have. So we have E minus V now. The graph of E minus V against I. So the first thing we draw the axis. So the first thing now we draw the axis. So we start with the y-axis. The y-axis. You have to be very accurate. So we have the y-axis with an arrow. Then we have x-axis, again with an arrow. So we are trying to plot a graph of E minus V against I, which we have already plotted. Then we are trying to determine the gradient of the graph. So we pick at least 2 readable points on the graph. We pick at least 2 readable points. Let's say we can pick this point here. You have this point, another readable point. Let's say we pick this other point here. So let's mark these points. These are the 2 readable points. The 2 readable points here. These are our 2 readable points. So once we have identified the readable points, let's say we can read them now. So this one is, these are 10, 20, 30, 40, 50, 51. 51 times 51 squares times 0.01. That is 0.51. 0.51. Then this one is 1.5. Then for this other point here, we have these are 12 times 0.01, that is 0.12. 0.12. These are 10, 20, 25, 28. 28 times 0.02, 0.56. So it is 1.50. These are the points of our graph, the ones we'll be using to determine the gradient. And once we have that now, slope, let's find the slope. So we know slope of this graph now will be given by, slope is equal to change in E minus V divided by change in current. Change in E minus V divided by change in current. So that means change in E minus V will be 1.50 minus 0.56 divided by 0.51 minus 0.12. So let's see. 1.50 minus 0.56. Get the answer, divided by, into bracket, 0.51 minus 0.12. And this one gives us 2.4103. 2.4103. We also need to know what is the value of the unit of this slope. So what we do, because we are dividing E minus V in volts, divide by current in ampere, that means voltage over current must be in ohm. Because in Ohm's law, we know V over IA is the resistance. And then we are given that EMF equals V plus IR, determine the internal resistance. So we know we can rearrange this equation to be in the form of Y is equals mx plus C. So that means we take V this side, and then it becomes E minus V is equals to I R. Already we have E minus V here, and we have I. So if you look at this equation, it is in the form of Y is equals to mx. But definitely We can also divide both sides by current. To simplify this again, this one becomes E minus V divided by current is equals to internal resistance. E minus V divided by current is equal to the internal resistance, and this simply implies that slope is equals to internal resistance, because E minus V over I is slope. We have the slope here, E minus V over I, which we still have here. And that means the internal resistance of these cells is 2.4103 ohm. So that becomes now the value of the internal resistance of these cells as per the graph we have been able to plot. So that marks the end of today's session. Stay tuned and we will meet in the next video.